Okay, we have another invited talk, this time from Marcelo Arenas. So Marcelo Arenas is a professor at the Department of Computer Science and the Institute for Mathematical and Computational Engineering at the Pontificia Universidad Católica de Chile. He is a fellow of Association of Computing Machinery and was the director of the Millennium Institute for Foundational Research on Data and the Center for Semantic Web Research. He received his PhD from the University of Toronto in 2005. His research interests lie in the areas of data management, applications of logic in computer science, and the semantic web. He has received several distinctions, including an IBM PhD fellowship, an honorable mention in the 2006 Sigmund J. Gray Doctoral Dissertation Award for his PhD dissertation, Design Principles for XML Data, the 2016 Semantic Web Science Association 10-year award for the article Semantics and Complexity of Sparkle, a 2020 ACM Sigmund Research Highlight Award, and 9 Best Paper Awards at major conferences. He has served on numerous program committees and editorial boards, and he chaired the program committees of several important conferences. He had also participated as an invited expert in the W3C and OECD. So, yeah, without further ado, I'll leave the room to Marcelo Arenas. Thank you.
So, can you hear me, right? Yeah. So thank you for the introduction and thank you for the invitation. It has been a really lovely week. And just in particular, we have a really interesting experience biking. Okay, so what I'm going to talk today is about explainability. It's related to what we have been hearing today, but probably I'm going to follow a different approach. So I suppose here I don't need to convince anyone that there is a great interest in developing method to explain prediction made by ML models. I mean, essentially, the ML models are black box, right? So we have these models that are giving answers, and we don't know why they're producing these answers or these scores. And so this has led to the introduction of a large number of different queries and scores for explainability, right? And what we are doing here is we're focusing on formal explainable AI, which you could say it's a growing area that is trying to develop notions of explainability that have some mathematical guarantees. This is similar to what we heard in the previous talk, right? For example, when we have rules, right? So we consider these rules as an explanation, and these rules, they have a formal semantics, right? This is as opposed, I mean, the distinction is not that clear, right? But this is as opposed, for example, to some explainability method that use, for example, scores, right? They also have a formal definition. If one looks, for example, for the CHAP score, they have a formal definition, but they have different guarantees. So let me show you some examples of what I'm talking about and what I want to do. So for example, this is a very simple, I mean, I will be using always this decision tree. This is a very, oops, it has color in my, doesn't matter. The colors are not that important. So this is just a simple decision tree about the credit, whether I'm going to get the credit or not. I will be using this as a running example. I mean, what I'm going to talk is applicable to other models, but this is a very simple example. So the idea here is, remember, we have 4 variables: a stable income, whether we have a stable income or not, whether we have a good credit history, whether we have low debt, and whether this person has collaterals, right? So for example, if someone has a stable income, which means that in the root we have 1, and then a good credit history and low debt, so all the ones there, then the answer of the decision tree is true, you're going to get the credit, right? If you don't have a stable income and you don't have a good credit history, like 0, 0, then it's false, you're not going to get the credit. And I'm going to use these simplifications, right? So these are the values that I'm going to use is I, H, C, and D, right? Income, oops, I forget one, yeah. Credit history, sorry, history is the H, collateral is the C, and D is the debt. Okay, let me remember that. I mean, the letter is not so important, but remember that it's useful actually when you are thinking about this decision tree. Okay, then, so suppose, for example, you get the classification, right? So in this case, we know for that person that everything is 1, which means that it has a stable income, it has a good credit history, and so on, right? So you say, yes, we have classification 1, and one way to think about this in this tree is you can prune the zeros, right? So you can do something like this. All the zeros that do not apply, there is some part of the tree that is not reachable, that you don't care about, and at the end, you just get this path here. So this is the result actually true. In this case, you are going to get the credit. But then you can ask, why was the credit approved? I mean, do you really need to have 1 in all the variables? Maybe it was not necessary. And how can this decision be changed actually? What changes in this variable would make that my credit is not approved, right? So this is the kind of question that one would like to ask. And for example, in the case of Y, so you think about this classification, but now let's say that you remove the collaterals. You just keep the other values. So for C, you don't know whether it's 1 or 0. So again, you prune. You are going to prune these, but for I, H, and D, you are going to eliminate the zeros. But for C, actually, you keep both values. Again, you have to remove the part that is not reachable, and you get again true, right? So you say, yes, it was enough to have a stable income, a good credit history, and a low debt to obtain the credit. Yeah. And this is what's called abductive explanation. This is a way of explanation that, or a form of explanation that is widely used in the literature. It has different names, right? But it has been used for a long time. And obviously and this is a local explanation, right? This is a local explanation for the positive classification of this particular instance. So, for example, there are other alternatives. If I just say I equal to 1 and C equal to 1, again, in this process, remove for I and C the 1s, right? And then remove the part that is not accessible, and now you don't get the path, you get the tree, actually. So you have different alternatives, but all of them lead to true, right? So again, you're saying that with the stable incomes and collaterals, right, if you have a house, for example, right, then you're going to get the credit. Okay, so this is the Y. This is again an abductive explanation. It's smaller than the other one, right? Has less theater, so you could say it's a better one under some minimality criteria. Okay, and now the how. How can you change the value actually? So, for example, what could happen actually that would change the value of the classification? So let's think about this D equal to 1 and C equal to 1. Again, you do this pruning process. But now when you do the pruning process, and you remove what is not accessible, right? The C down there. So then you get this tree, and then you're going to have that path. And that path leads to false. So you are saying if you change the value of I to 0 and the value of H to 0, and you keep D equal to 1 and C equal to 1, you are going to change the value of the classification, right? And this is what is called in the literature a contrastive explanation. Again, widely used, actually widely studied, has been studied in many different contexts, and is considered like a very reasonable way to think about, like, or to try to explain what the model is doing. Okay, so this is, again, is a local explanation for the positive classification of the instance. And for example, you also have global explanation. The last example that I'm going to give about these things, for example, what is a global explanation? A global negative explanation is something that you know that the model is always going to give you false if you have these particular values, no matter what happened with the other values, right? So what you're saying is you have I equal to 0 and Z equal to 0, right? You prune and you remove what is not reachable, and then you see that you end up with this tree here where everything is false. So no matter what you do with the other variables, if you don't have a stable income and you don't have a house, collaterals, then your classification is going to be false, yeah? You're not going to get the credit. Right, so this is like a global explanation. You are saying for the whole model, actually, you are getting false. Okay, so the main issue here is that formal explainability does not admit a silver bullet. There is no one notion of explanation that is universally considered as the best notion of explanation. There is a lot of debate whether we should use this notion, whether we should use Chubb's scores. I think it was last year, there is a very interesting paper, which is, I think it's called Explainability is Not a Game, where what we did is compare these notions with Chubb's scores and show examples where the Chubb score give very counterintuitive results, right? Like you get a very, Chubb score could be positive or negative, right? When you get a positive score, it means that you are somehow helping to the classification, right? Negative score is the other way around, yeah? So you were, like, for example, getting high score for variables that were not relevant. You were getting negative scores for variables that were very relevant. So I mean, there's a whole debate of what is the right notion. So how do we deal with this increasing number of explainability notions? So our somehow idea is that explainability may require combining different notions of explanation. You can think of this, it's better to think of this as an iterative process, right? Since there is no A notion, maybe a user wants to use several notions of explainability. Why not to provide the user with a language that can use to like pose this as a query, right? Let's say you pose one query and then you want to use a different one. You say, okay, I want to use this notion. I want to combine it with that notion. This is the kind of thing that we know how to do in the database community, right? This is what we have been doing since the 70s, right? Developing query languages. And once you have that also, yeah, you don't need algorithms. Like everyone who develops a notion of explanation has to develop an algorithm, hopefully an efficient algorithm to compute this notion, right? If you have a query language, you can focus on optimizing the language again, right? You just need to write this explainability notion in this language. Hopefully, it's going to be declarative, and then the system takes care of evaluating this particular notion of explainability, right? So this is kind of the idea that we have, right? Let me just give you some more examples, but examples that you will see actually that resembles a query language, right? For example, you have two different classifications that give you one, and then you ask whether there is a common adaptive explanation for both, right? So obviously not a good way to do this is to compute all the possible adaptive explanations for the first set of theaters and then try to see which one it's an adaptive explanation for the second, right? This will be very expensive, right? But again, I mean, maybe you can come up with the efficient algorithm for this problem, but then you will have the next one, right? And you will say, okay, I don't want to continue doing this, like developing more notions of explanation, developing more algorithms. For example, in this case, there is an answer. I see it's an answer to this query. But then, for example, you can say, like, is there an adaptive explanation for the positive classification of the first set of theaters that is not an adaptive explanation for the positive classification of the second, right? You want something that distinguishes the first classification from the second classification, right? So then, yes, the answer is yes, but think about like developing again an algorithm to do this actually. And there are lots of other alternatives, right? Is there a theater assignment that is necessary for the positive classification of this input? For example, this is a global query. In this case, I equal to 1 is necessary. If you change that, you're not going to get 1. And well, there are many more of these queries. Let me show you. The other thing that can happen is that you can think about different orders. I will think about minimality up to this point. Well, I haven't mentioned that much, but the notion of minimality, but you can think about minimality in different ways, right? Like containment, right? Like set containment, but you can think about also about cardinalities, right? I want the explanation with the smallest number of theaters, for example, right? So there are different orders, and not only that. So for example, you can ask what is the adaptive explanation with the smallest number of theater assignments for the positive classification of these, actually on same thing with the global adaptive explanation with the smallest number of theater assignments. And then you can see in the literature that while you are moving into this, actually, people, for example, assign preference to theaters, right? This theater is more important than this one, so when I consider my order, I have to take that into consideration. Again, you have another query, right? That you are saying, okay, this is more important than this. When I have the order, I want to compute the minimal. And it gets, I mean, if you want to read the literature, you're going to find lots of these papers, right? With like interesting notions of explanation, interesting algorithms, but essentially this idea, right? Like you're getting better and better notions. So in our case, you can say that it's like a call for an explainability query language, a language where you can express all these things, right? So clearly these previous queries, I mean, resemble traditional queries in databases, right? And in particular, some operators are needed to combine explainability queries. And okay, so something I will try to do here is just give a desiderata for one of these, for a language, right, for where you can express explainability notions. So something, I mean, all the things that I'm going to say apply to query languages, actually, what we have understood about query language over the years, right? So I'm not saying anything really new here. The first thing is that the language should be declarative, right? I mean, we want something that with a simple syntax and semantics, something that where you can say what is the notion that you want to evaluate, the notion of explainability, but you don't need to say how you are going to evaluate this notion, right? And it should be based on well-known database query languages. We're not going to reinvent the wheel, right? It should be based on, first of the logic, relational algebra, the things that we know well, right? The second thing is that there should be a one-to-one correspondence between queries in the language and explainability notions. And in particular, what we want is that an explainability notion should be represented by a fixed query. We don't want something like, okay, we have a model with some dimension, we write an adaptive explanation, and it's this query, but now the model has, I don't know, before it had 10 theaters, now it has 20 theaters, and we have to rewrite the query, right? We want one fixed query that represents adaptive explanation that can be evaluated over all possible models, right? And when it gives me an answer, it's an adaptive explanation, right? Or it's a minimal adaptive explanation, right? So this is, for us, is very important, right? Okay, in terms of expressiveness, well, the common explainability notions should be expressible in the language. This is sort of a test, right? We are going to develop a language. We know that there is a trade-off between expressiveness and complexity. If the language is too expressive, right, probably it's going to be very difficult to evaluate. But if the language is too weak, we are not going to be able to represent the common notion of explanation, right? So there is a trade-off there, and we need a balance, right? Also, it should allow the user to explore an explanation concepts, things like we were doing before, right? Let's combine two notions of explanation. Let's think about the distinctive notion of explanation, something that is an explanation for in this case and not in that case, and so on, right? In terms of efficiency, it should be possible to evaluate every query in the language efficiently. Notice that now we're talking about when database is called data complexity, right? A notion of explanation is represented by a fixed query. So we should be able to evaluate every fixed query, hopefully in polynomial time. But here, it's not going to be polynomial time because we know there are notions of explanation that cannot be evaluated in polynomial time. For example, if one thinks about minimum adaptive explanations, for example, right? So our target will be not the usual polynomial time, like when you think about, like, I don't know, first of the logic, like data complexity is polynomial time, or relational algebra data complexity is polynomial time. We're going a bit higher because there are some notions that are inherently difficult, and our target would be P to the P. The only thing I'm saying there is that what we'll want to have is an polynomial time algorithm that could use a SAT solver as an oracle, right? So it's a polynomial time algorithm that can do some calls to a SAT solver, actually. This is our target. We have done, I mean, what I'm going to show you is implemented, and it works well, thinking that a decision tree, well, you can use over the model, is not of the size of the database. It's not going to be a 2 gigabyte decision tree, right? So this could be considered reasonable, right? In particular, I want to point out the last thing. I mean, SAT solvers are a really nice technology, right? So they work very well, actually, and they have been a lot of help in this case. And again, the first point, the second, certain explanation tasks have an inherently high complexity. So, I mean, there is no way that we can avoid that. We write them in the language, and the language will not be able to evaluate this in polynomial time, right? So that's why that's our target. And, well, this is our goal then, to develop an explainability query language that meets the previous criteria. Okay, so let me show you how we are going to do this. So to construct the language, we need to do two things, right? First of all, we have to say how an ML model is encoded in a database, right? We're thinking really about the query language, right? There are different ways in which you can do this. We're going to show how to do that. And the second thing is like, we have to show how an explainability task. I'm going to come back to the examples at the beginning, right? I'm going to show you how we write them in the logic that we have been developing, right? But remember, these two things. So we need to represent the model, we need to represent the queries. Okay, so let me give you a first attempt on the encodings, and this probably will be like the simplest one, right? If you have a decision tree, let's think for the time being on the decision tree. This is a graph, right? We know ways to represent the graph as a relational database, right? We can use, this is a label graph, so we can use a ternary relation for the edges, we can have a table for the nodes, right? We need to store the labels, right? We have, if I remember correctly, 8 nodes here, right? We need identifiers for these nodes, and then we have to say that, for example, for the node in the root, the label is I, these kind of things, right? This we know how to do, actually. We can do it with the relational database, we can do it with the graph database, right? So one would say, okay, why not to do that, right? So we will do something like this. We have here node identifiers, right? And then we have something super simple like an edge table where we have the node label node. So for example, the first edge there represents the fact that 1 goes to 3 and the label is 0, right? So this is what we have there. 1 goes to 3 and the label is 0, or 1 goes to 2 and the label is 1, is the edge on the top that goes from 1 to 2, right? I mean, really, really simple, right? You can have a table where you say, for example, this node is not a good notation, sorry, it should be labeled, right? We are saying what is the label of each node, right? The label of 1 is I. You have to remember this is the theater that this number represents, 2 each age, 3 is age, whatever. You have to say what is the root, right, which is 1. And then, how do you specify the input? Remember that something that we want is that the explainability notions are expressed with a fixed query, right? It's not like we are going to change the query if we have different dimensions, right? If instead of having 4 theaters, like in this example, we have 5, we don't want to write a different query. So the input is easy to specify. You can have like a table where you have something like this, right? You say what is the input, which means for every theater, what is the value that you have, right? For the, I don't know, stable income, you have 1. For the low debt, you have 1. So you put that in a table, very simple. And if you have that, and this is for the relational AI audience here, you can write that in a nice language, for example, in QB, in relational AI, right? This is a set of rules, fixed set of rules that will evaluate this previous representation, right? And I mean, I'm not going through the explanation, but it's a rule language, actually. It's a typical rule language, actually. You run this recursive program, and you will get the value of the tree for these particular assignments for the theater, right? So, I mean, there is an easy way to represent these things, actually. This is fairly standard, I would say. But then when you start thinking about what does it mean to represent an explainability notion, like explainability notions are reasoning about subsets, right? We're saying we have a set of theaters, and now we are going to think about a subset where, for example, we are going to undefine some of the value. We're saying, okay, now we don't want to say that H has value 1. We want to play with the idea that has value 1 or 0, right? So when you start thinking about that, the natural, what you are going to do on top of that, or the natural way to do it, is to put second-order logic, right? And once you put second-order logic on top of this, everything is going to be expensive, right? Data complexity is no longer going to be, well, we want P to the P, actually, but we are going to be higher than that, right? We're going to have all kinds of problems. I mean, I'm not saying that it's not possible to solve it in this way. I'm saying that we don't know how to solve it in this way, right? So, I mean, it could be a way to, could be a good problem to think about, actually. What kind of logic can you put on top of this, like, recursive representation in order to get all these notions of explanation, right? Okay, so that's not what we're going to do. So what we have been doing is the following. Let me show you now the logic that we have been developing. So first of all, it's model agnostic. It's not a logic defined for decision trees. It's defined for classifiers in general, right? Now we're going to talk about Boolean classifiers. You can move to classifiers that are not Boolean, actually. For example, I don't know, something that is probabilistic. It can be done, actually. But in our case, at this point, actually, we're going to do it for the Boolean case. And then we have an abstract definition of all these things that we need, right? So a model is just a function that takes, it goes from 0, 1 to the end. You take n theaters. For each theater, you take a value. It's 0 or 1, right? 0, 1, 0, 1, 0, 1. And then you say 0 or 1, what is the classification, right? So the classification model is just a Boolean function, right? That's the way that we represent this. An instant is a basic object. Actually, we are going to be reasoning about instances all the time, right? So an instant is just an assignment of values for the theater, right? In our previous example, n was equal to 4, right? So we have instance with 4 theaters, and here we are giving values to each one of these theaters. And the other thing is that, well, we have this abstract notion of when this classifier accepts E, and this is the case if m of E is equal to 1, right? You run this Boolean function, and you obtain value 1. Otherwise, m rejects E, okay? This is a general notation. So then, okay, this is based on a paper that we published in NeurIPS in 21. It's in the reference, actually, you will find the paper. But the idea that what we were trying to do is the following, actually. So we just want to use first-order logic. We don't want to move from there, right? The key issue then is what is the suitable vocabulary to describe classification models, right? That's what we need, right? But we want to stay in first-order logic. We don't want a new logic, right? Not even recursion, right? Just first-order logic. So the first ingredient is, given a dimension n, the instances of dimension n are the objects stored in the database. We're not going to store particular values. We're going to store instances. Remember, an instance is a vector with n values that tells you for each theater whether you are 0 or 1. These are the objects that we want to store in the database. We have a large number of these objects, so we have to be careful. We have to deal with all these issues, right? And we'll have something like a predicate that tells you for which one of these instances you get value 1, right? For which one of these instances the model gives you value 1. Okay, let me show you this in the example again. So we have something like this, right? This is our decision tree. So assume some order for the theaters, because, I mean, we are going to have a vector, right? So I have to say this value 1 corresponds to which of the theaters, right? So this is the order, I, H, D, C. And then you are going to say in this table pos, you are going, the objects of the table, this is not a table with 4 theaters, it's a table, sorry, it's not a table with 4 columns, it's a table with 1 column. And in that column, you're storing instances that satisfy this model. So for example, the first object there is 1, 1, 1, 1. This is one instant. And this instance, if you put it in this classifier, is going to give you a value true, right? The second one is 1, 1, 1, 0. Also, you put it here, is going to give you value true, right? Obviously, at this point, you are thinking that this is going to be of exponential size. Yes, that's true. It's going to be of exponential size. We don't want to materialize this. I'm going to come back to this, actually, right? Yeah, but think about the model at this point, actually, because really we need the model to give a semantic to the logic. Okay, so in this table pos, you're going to put all instances that are classified positively by the model. Okay, this is the first ingredient that we need. And the second ingredient that we need, actually, and this is sort of the key thing for this logic, is that we are not only going to consider instances, we are also going to consider partial instances. And a partial instance is an instance where you can have some undefined values. In all the notions of explanation that I show you, and in most of the notions of explanation that are coming from formal AI, you reason about some undefined values. You say, what happened if this value doesn't, if this theater doesn't have a value? Am I going to obtain always a positive classification, right? So to do that, what we're going to do, again, in the tradition of databases, we're just going to introduce a null value, right? We have this bottom notation there, so sorry, a partial instant is just a vector in this set 0, 1, bottom, right? This is a symbol that says it's undefined, no more than that, right? We don't know what is the value for this guy, right? Okay, so we have that, and then, okay, something to say is like positive of E is false if you contain an unknown value, right? Post is just a value that we use for the instances. It's just a decision, right? It's just a decision to say, post is used to say whether an instance, a complete instance, is classified positively or negatively by the decision, by the model. So we decided that it's false for anything that has some undefined values, right? You can do it in a different way, yeah? But this is cheap, right? It doesn't have any cost, actually, when you want to evaluate this predicate, okay? Then the second important thing, actually, that we need is an order on partial instance based on the notion of being more informative, right? More informative means that here you have an undefined value, and you're more informative if you give me a value for that guy, right? So it's a very simple subsumption relation that is defined in the usual way, right? Like you say that E1 is subsumed by E2 if for every position such that E1 of I is different from bottom, you have exactly the same values, right? So in an example, for example, the first instance is subsumed by the second because for the position where you have values, you have exactly the same values, but also for the first bottom, you assign a value on the second tuple. You assign value 0. So you have more information in this case. You're giving me more information. And again, this, the last tuple there is more informative than the second, and this is transitive and it's more informative than the first because actually you have values in all the positions, right? So it's like for the undefined, you are giving values. Okay. So so then you can think that in the database, you have something like this subsumption predicate. Again, this is going to be huge. We don't want to materialize this, but for the time being, just think about this in terms of the semantics, right? Or you can think of this as a built-in predicate, something that you can use and evaluate. But it's a table, a binary, and remember, has 2 columns, right? Because the objects that we are using here are the instances. Okay? So then a model M is represented as a relational database DM, which is going to be this one, right? So I'm thinking about the previous example. So what you have to do is you have to put the what is positive and the subsumption, right? These are the 2 relations that you are going to have in your database. So you start from the model, very abstract, it's a Boolean function, and you end up with this database here. Okay. So very simple. So then the first logic that we are using is just first order logic defined over this vocabulary, just pos and subsumption, no more than that. Okay, obviously evaluating the query is going to be challenging. We are going to talk a lot about that actually, but it's as simple as that. You just want first order logic, where when you quantify, then you are quantifying over instances, and the predicate that you can use is pos and this subsumption there. Okay, and then how is the semantics defined? And this is the reason why we are using this database, is defined in the usual way, right? Like now we have a formula, right, phi, that has 3 variables, x1 to xk. Each one of these variables is going to be evaluated over instances. You're going to replace x1 by an instance, right? It's not like we're saying x1 is a theater. No. It's always instances, right? And you say that a model a model of dimension n satisfy this formula for instances E1 to EK, and this is the notation, and the nice thing about the previous definition is that you rely just on the semantic of first order logic, right? You say, okay, if the database, this large database that we define with subsumption and pos, satisfy the formula, right? So it's usual semantics. We're not reinventing anything. Very simple, right? It's just the usual semantic of first order logic where you have a representation for the model, right? Okay, let me show you the examples, and hopefully I will manage to convince you that this is a good way to write them, or maybe not. But okay, let me show you some useful formulas first that will be using something like properly subsume, right? X is subsumed by Y, but Y is not subsumed by X. We need to, in our language, we're going to have the instances and the partial instances. This is part of the domain of the database. So we need to have a way to distinguish them. And this is definable in the logic. So if you use a formula like this one, instance of X, it means that for every Y such that X is contained in Y, X is equal to Y, this means that Y has to be an instant. It cannot have undefined values, right? So something that doesn't have undefined values, it doesn't have any, it's not properly subsumed by anything. That's what we're saying, right? Some comment about this. We're not thinking that the user is going to write something like that, right? Obviously, on top of that, you are going to have like a user-friendly language, right? But what we wanted to have is like a well-defined language, and that this like high-level language can rely on, right? Everything will be rewritten in a language like this. Okay, so still useful formats. And you can talk also about like all pos, which means what we're thinking is that we have something that has an undefined values, and no matter how you assign values to these undefined positions, you are going to get value 1. That's what we're saying there. So what we are saying is for every Y such that X is contained in Y and Y is an instance, it doesn't have undefined information, you know that Y is positive, right? So you have some undefined values, and no matter what values you assign there, you're going to obtain value true, right? This is all pos. And then we have something like all neg, no matter how you assign values, you're going to obtain a negative classification, right? No matter how you assign values to the undefined values of X. Okay, why we need this? Because now I can show you the examples, right? So, for example, if we want to write abductive explanation, and again, think that we want to have a fixed formula that can be evaluated over a model of any arity. So, okay, so the idea will be the following, right? So, remember that we have these 4 theaters there. I'm going to use that as an example. Remember that we classify this 1, 1, 1, 1 as 1, and we, well, in the example, we saw that this vector E1 there, actually, or this tuple E1 there with 2 undefined values was a abductive explanation, so we want to somehow get that answer in our logic. Okay, so how do you represent this? As follows, actually. So first, you need a formula that tells you that something, okay, let me read the formula for you. So we have alpha of xy. X is an instance. So X is something that we want to explain. Y is contained in X. So what we are saying is, for y, we could remove some of the values. So for example, here e is x, is 1, 1, 1, 1, everything is defined. Then e1 is contained in e. This means we could take some of the values of this instance and replace it by some undefined values, right? And what we want to say is when we do this, we obtain exactly the same classification. So what we are saying, you are an adaptive explanation if you have this adaptive explanation for this classification. Suppose the classification is 1. If you undefine some of the values, and now you start thinking about, okay, I replace these values, what I'm going to obtain, if I always obtain 1, it means that these values were enough to obtain the classification, right? So that's what we are saying there, right? We are saying x is an instance, y is containing an x, and if x was positive, all pos of y. Remember that all pos of y means every completion of y, no matter how you complete the values, you are going to obtain positive, right? So this means that you are what is considered an adaptive explanation, right? With those values that you keep in y is enough to explain the positive classification of x, right? And you are doing the second thing in the last case, like, well, if it was classifying negative x, then you have all x of y, right? Okay, this is a fixed formula that represents adaptive explanations. And for example, if you want to write minimal adaptive explanation, which is usually what you want in practice, you have to write something like this, right? It's very easy because minimality is easy to express in first order logic, right? You say something like alpha of xy, so y is a adaptive explanation, and for every set such that alpha of x set, for every adaptive explanation, it could not be the case that set is properly subsumed by y, right? So we are saying it's minimal in terms of set containment in this case, right? So this here is a fixed formula that you can use to talk about adaptive explanations, in particular the minimal adaptive explanation that we have there, right? So what we are thinking is that once you have these, right, the formula there, okay, this one, right, you can evaluate this query as any database system, right? And when you evaluate the query, you would expect to get, for example, if you are evaluating this query, you are saying, okay, give me all the possible classifications and adaptive explanation. Probably you are going to give the first parameter. It makes sense, right? To say E and give me the possible adaptive explanation. That's what you expect to get, right? So in this particular case, for example, you can see that the decision tree satisfies this formula for E1, right? So E1 is an adaptive explanation, right? Okay, let me show you a second example. Contrastive is essentially the same idea, right? Now you are saying we have an instance x, y is containing an x, and remember that contrastive means that for this y, there is a way to obtain a different result, right? We have this classification which was 1, we have this that is contained with some undefined values, and there are some ways to assign values to this such that you will obtain a different value, right? That's exactly what you are doing there, right? You are saying y is containing in x, and if it was positive x, then not all pos y, it means that some of the extensions will be negative, or if it was negative x, not all neg y, which means some of the extensions of y will be positive, right? So this is what you call a contrastive explanation. And this, for example, is, well, contrastive explanation when you consider minimal is what we have in red there, right? Again, we write this with a fixed formula, right? And then, if we were thinking about, okay, and then it's very easy actually what we were saying before, like common adaptive explanation. We want an adaptive explanation for these two instances. What you have to say is like, y is a common adaptive explanation for x1 and x2. It's just a super simple query, right? It's an adaptive explanation x1y and adaptive explanation x2y, right? You just write this in the language. Or if you want a distinctive explanation, right? So now we are saying y is an adaptive explanation of x1 and it's not an adaptive explanation of x2. Just first order logic, the usual stuff, relational algebra, set difference if you think about relational algebra. So you can start writing all these notions, right? Like global necessity of effect theater, I'm going to mention this because I will use in another example. You can write, until what time do I have for the presentation? 10, 15 minutes, okay. Okay, so remember that this global necessity of a theater is essentially saying, for this theater, we need to have some value to obtain some classification. For example, like, you need to have a stable income to get a credit. If you don't have a stable income, no matter what you do, you're not going to get the credit, right? So we need value 1 for this. And then we have to talk about theaters. But this logic doesn't allow you to talk about theaters directly, right? You are always talking about instances. But there is a simple way to talk about theaters. Again, in the high-level language, you will have quantification over theaters. You want something user-friendly. But this language is not needed, actually. And why is the reason? Because you can do the following. This L0 of x tells you that this is the bottom element, the element that is contained in all elements, right? Just bottoms, right? And then by using this, you can define the elements that are in the second, if you think of this lattice, like going from everything undefined to the instances where everything is defined, right? You're thinking about the second level here. And the second level is this L1 that tells you are one level up from L0, right? So these are the kind of elements that you have there, right? You have one theater that is defined, exactly one, right? So if you think about the elements of L1, these are the theaters. So if you quantify over these elements, the elements that satisfy L1, you're quantifying over theaters, right? So you can do that, actually. So we can then write things like global necessity. Now we're saying global necessity of X, we're saying this theater is necessary to get, in this case, a positive classification. But we're not talking about, it's not like now X is a theater. It's again an instance, but it's an instance that satisfies L1 of X. So we know that there is exactly one position that is defined. So it's a theater, right? Again, in this low-level language that we're defining, in the user-friendly language, this should be explicitly a theater, right? And what you're saying is that we have L1 of X, and for every Y that is classified positively, X should be contained in Y. So when we say X should be contained in Y, we're saying this theater that we have here that has value 1 or 0 in X, you should keep the same value in Y, right? Like what we were saying, like in order to get the credit, you need a stable income, you need value 1 for I. So in X, in the stable income, you have value Y, and since X is contained in Y you should have that value, right? So you're saying we have to keep this value. Okay, so let me tell you a few things about the expressiveness and complexity. I'm not going to have time to go through all the material, but the thing is that a couple of things that are important is, well, first, what notion of explanation can be expressed in FOIL? This remember, is like the first version of the logic. What notion of explanation cannot be expressed in FOIL? That's also very important. And what is the complexity of the evaluation problem for FOIL? And this complexity is data complexity. Since a notion of explanation is represented by a fixed formula, we're thinking we have a fixed formula, and we want to know what is the complexity for this fixed formula. Okay, so let's first define then the evaluation problem. So the idea is that we consider the data complexity, so we assume a formula phi, right, which is a fixed formula. And then we have a value of phi. Phi is fixed, that's why I'm using that notation. And the input then is going to be a classification model, this is part of the input, at the partial instances that you can use. I mean, this could be instances where everything is defined, or instances where there are some undefined values that are going to use as input of this formula, right? And then the output is, in this decision case, if yes, if M satisfies this formula, and no otherwise. It's the typical decision problem for a logic, and in particular data complexity, because the formula is fixed. And the bad news is that the complexity is very hard, and even for decision trees, actually. Now we're proving like lower bound, and the lower bound is going to be really high, even for very simple machine learning models. Actually, if you move to more complicated things, it's going to be even worse. So, okay, so what can be proved is that for every FOIL formula, there exists some case such that this problem, the value of phi for decision trees, is in that level, in the level K of the polynomial hierarchy, but you also have hardness, right? For every level of the polynomial hierarchy, you can have, or you can find a FOIL formula phi such that a value of phi for decision trees is sigma kp hard. So you are hard for every level of the polynomial hierarchy. And as you can imagine, the main problem is that you can alternate the quantifiers, actually. But remember that this is data complexity, right? This is not inherited from first order logic, right? First order logic has polynomial data complexity, which is lower than that, right? This is 0. Here is because of something that is a bit tricky, which is that in order that we are given a decision tree, right? So in order to evaluate the query, something that we cannot do is to materialize the database and then evaluate the query, right? Because the database is going to be of exponential size in the size of the decision tree, right? So something I forgot to say is that when you consider this problem, you have to consider the input given in some format, right? That format is not going to be the database because this is of exponential size, right? It's really going to be a decision tree, a circuit, whatever, actually, and you have to use that, actually. And that makes the problem harder, actually, and that's why you get this, like, really high complexity. And the other thing is that the logic, which I suppose is not really surprising, is missing any capabilities to count, essentially, or to compare cardinalities, right? And something that is important in this area is also the idea of finding minimum explanations with the minimum or the maximum, depending on what you are doing, number of theaters, right? So this logic doesn't have that capability, and it can be proved that, for example, there is no FOIL formula that can express minimum abductive explanation. In this case, you are looking for the abductive explanation with the smallest number of theaters. So there is no way to express that even for the class of decision trees, right? Which is not surprising, right? You have a lattice, you have all these, like, I don't know, finite model theory results for lattices that can be applied here and show you that you cannot do this. Okay, so there are problems with this. So then the question is how to overcome these limitations. And I don't have much time, so let me try to give you the idea. So there are several things that you can do, like extend FOIL vocabulary to express missing notion of explanation. So we need some predicate to compare cardinality. We could extend the logic with those predicates. The other idea is to identify fragment of FOIL that can be evaluated efficiently, right? Something like, let's just consider the existential fragment or the universal fragment or something like that, right? Or depart from the model agnostic approach, right? So here model agnostic in the sense that we are considering a classification model just as a Boolean function. But we could say, okay, why not use decision trees and let's try to encode the decision trees, for example, the notion of nodes or lived, whatever, actually in some way, right? Okay, this is what we are going to do, but something we don't want to do is something like this, right? To end up with what we call plumbing, right? You add something here, you need this here, you put this here, and at the end you have a horrible language nobody understands, right? So we really want to do this in a more principled way. By the way, this picture was generated by ChatGPT, actually. Took me some time, but yeah, it's a good picture, yeah. This is like plumbing in Chile, right? Yeah. Okay, so the idea is the following. So what we want to do, okay, I have very little time, but essentially two ideas to remember. We want to extend FOIL to express missing notion of explanation with the minimum number of predicates. We don't want to add the predicate every time that we're missing something, right? That doesn't make any sense. And we want to depart from the model agnostic approach, but in a way that we consider more principled, right? In a way that has been done before in logic, actually. We don't want to start introducing strange constraints, right? And this is essentially, but there is more work, actually, something we presented in KR this last year, but what we have here is like the next version, right? Okay, let me just give you an idea of how this works. Extended the vocabulary, obviously we need this sort of cardinality comparison. So again, if you think about the lattice, like you are talking about the levels in the lattice, right? You are saying E1 is contained in E2 if the number of undefined theaters in E1 is greater or equal than the number of undefined theaters in E2, right? It's a very simple predicate. And then obviously it's easy to express something like minimum abductive explanation, right? It's the same formula as before, but now you're saying that y is a minimum abductive explanation of x if it was satisfy alpha, and then there is a set such that alpha of x set, and set has a larger number of undefined theaters, right? This will be like a lower number of defined theaters, right? Super simple, okay? The question now is, well, are we going to continue this, actually, doing this, actually? Like, we are missing this, we are going to add another predicate. And then I think is that that's not necessary, like all the order predicates needed in our formalism can be expressed as first order queries over these two predicates. And in particular, I'm saying needed, in our case, it means for the usual notions of explanation, for example, where you have things like different priorities for the theaters, or, for example, you want to use things like Hamming distance and you want to count the number of difference. All these things can be expressed with these two predicates, actually. So we're not saying that we don't have like a completeness result, right? No. What we say is that all the usual notions actually can be expressed with this. And the other nice thing is that this, when you think about a formula that is expressed just with these two predicates, this, and a class of classification models, any class of classification models, then a value of phi c can be solved in polynomial time, right? We don't have the post predicate, we cannot materialize this thing, and the thing is that it's a non-constructive proof, actually. You can rely on these Ehrenfrau-Freysse games, actually, to prove that essentially there is a bunch of models that you need to prove. You don't have that many models, right? Different models. There is a bunch of models that you have to prove. The only thing I want to remember from this is that it's possible in terms of data complexity to evaluate a formula that doesn't mention pos, right? So it's like a good starting point. And then on top of that, and I have like, what, 5 minutes? Less than 5 minutes? 3 minutes, okay. Okay, these are the atomic formulas, and you do two things on top of this, right? And you can do this in different ways, right? What you want to do, okay, I'm going to skip a bit this part, sorry. But what you want to do is to use guarded quantification, right? Again, we don't want to depart from the usual stuff. You can do this in many different ways. In KR, we were doing this like for decision trees, so we were thinking about quantifying, for example, over path in the decision tree, or over nodes in the decision tree, which is linear in the size of the decision tree, is not a problem. But here we're using our filters. But guarded quantification just means that every time that you say there exists an X, you say that there exists an X that satisfies some property and something, right? And if that property tells you that there is a polynomial number of these elements, then you're fine, right? You're not doing like something there exists an X such that X is a theater. You have an exponential, sorry, there exists an X such that X is an instant. There is an exponential number of instances, right? So it's difficult to evaluate that query. So the only thing, turns out that the only thing that we need really is to quantify at this level. So you have first level atomic formulas, then guarded quantification. We only need to quantify our theaters. Remember that this predicate L1 of X tells you whether X is a theater. So you're saying that X is a theater such that something, or for every theater such that something, right? So this will be like our first level. Okay, I'm going to go through this fast, sorry. And then with that, actually, what we know is that this is the general result, the logic that we construct there. If we know that all pos and all neg, remember, all pos means I have some instance with some undefined values, and I want to know whether every completion of that instance gives you a positive value. So if you think, for example, if you have a circuit given in DNF, you cannot do that, right, in polynomial time, because this is tautology, right? Or, right, if you have everything undefined. This is a complete, right? So it will not be possible to do that. But the nice thing is that if you consider a model of circuits or binary decision diagram where these two predicates can be evaluated, all pos and all neg can be evaluated in polynomial time, then this logic can be evaluated in polynomial time. Almost done. And I was mentioning this here. There are lots of models that have these properties, decision trees or BDDs. You can go to these DDNF and NF circuits. For all of them, you can evaluate this all pos and all neg in polynomial time. And the last, okay, sorry. And the last comment about the logic, okay, you have two levels. And in the third level, what you are going to add, okay, this logic is not ready. Right now, you are thinking that this is plumbing, what I'm doing, right? Still, we need some work. But okay, you have a third level, the atomic formulas, guarded quantification, and on top of that, you can put essentially the existential fragment or the universal fragment. You can do Boolean combinations of that, and then you are going to get a logic, and I'm going to finish with this, that represents all the common notions of explanation. Here you have a list of different notions of explanation that can be expressed, and also that meets the requirement, sorry, I have to skip this, meets the requirement of the data complexity that we wanted, that was to have a polynomial time algorithm with an oracle for a SAT solver. In this particular case, when you take this logic and you think about the valve problem, is the Boolean hierarchy, right? So you need a fixed number of calls to a SAT solver, actually, to solve the problems in this logic. And just as theoretical result, this is hard for every level. Yeah. Okay, so can I finish with the conclusions? Yeah, okay. So I just wanted to say something about, okay, a couple of things, actually, that I think are very important. I'm finished with this. That much work remains to be done. Developing a user-friendly query language, I think this is very important, actually, right? I mean, what I show you is like a core, but in particular, there are a couple of problems that I think that the community should be considering. One thing is how to provide an explanation, right? So the level of granularity of explanation depends on the user, right? I mean, it could be the case that the user doesn't want to know all these answers that we have intermediate results, whatever. Actually, we need something simpler, right? which is different from an expert that probably is going to need much more, actually, right? And the other thing is, how do we know whether an explanation is like sort of correct, actually, that is trustworthy, actually, right? What kind of information we can give about that? And the other thing is that this idea that we're working now incorporating probabilities, right, to have really not only a Boolean classifier, we think is something important. Thanks, yeah.
Thank you. Okay, Alessandro has to say something.
Yeah, I would like to make a comment. I think this is a prime example of, how a great researcher with a database and logic, database and logic minded, say, can take a problem and provide a very sharp understanding of the problem. So, yeah, I really appreciate the talk. Thank you.
Okay. Any questions?
No.
Thanks, Marcelo. It seems that some of your hardness results for FOIL are based on the assumption that the number of features is not really a constant.
Yeah, the number
which seems a bit strange for data complexity, because usually this is like a query size.
Yeah, it's query size, but remember that the query does not include the theaters, right? The query does not depend on the theaters.
Okay, it's like a schema size.
Yeah.
But then I wonder, have you considered what would happen to the complexity landscape if we either consider the number of features to be a constant or at least parameterized by the number of features? Would this make the complexity landscape more interesting or possible to study in a fine-grained setting?
I mean, if you fix it, I suppose that everything is going to be polynomial. But if you consider as a parameter, this could be very interesting, actually, right? Yeah, because you will understand how, it could even be fixed parameter tractor. I don't know, yeah, but could be, actually, yeah, definitely. But we haven't not considered that, actually. Good point, yeah.
Thanks.
Any other questions? Over there. Okay.
Thank you. Yeah, really nice talk. My interpretation of what you're explaining is like you basically gave us a way in first order logic to construct like lossless compressed representation of a specific execution of the actual model, like the decision model. And the decision model itself, like as database people, could also be represented in first order logic, at least in many cases. So is there a way of, like a systematic way of going from the individual explanations to extracting constraints that can be used to optimize the actual decision model? Because like in a way, if you run these explanations and you always find that these two initial features are completely, that's all what you need to make a decision, then you can skip evaluation of all the other stuff, right? Is that a thing that you can extract from these explanations in like an offline process?
Okay, that's a good question. Probably it can, actually. I don't know how to do it in generally, but it should be possible, actually. You're right, actually, yeah. I mean, all these notions, I suppose this is similar to the talk that we had before, when they were extracting rules to represent the machine learning model, actually, and they were saying that these rules should be equivalent, right? So this is, again, you have some rules that could tell you how to optimize this process, actually.
Right, because we know how to include like inclusivity constraints and stuff like that, right? Sławek is going to talk about that. And so if we can extract that from these explanations, would be pretty cool.
Yeah.
Thank you.
More questions? Okay. Nobody? Okay. Seems like no other questions. So let's thank the speaker again.